Hi, and welcome to the defense of my thesis titled Decentralized Multi-Agent Visual SLAM. Simultaneous Localization and Mapping, in short SLAM, is an algorithm that gives agents a sense of their environment. This was traditionally developed for robots, but recently we have also seen applications such as augmented reality. In this video, we see how augmented reality devices use SLAM to know where they are in a room. Thanks to that knowledge, they can then project a virtual scenery into the room. My thesis is on multi-agent simultaneous localization and mapping, multi-agent SLAM. This is a shared state of the environment for multiple agents, and it allows them to coordinate. For instance, here in this video, we see an interaction between a human and a robot that is enabled through multi-agent SLAM. In my thesis, I focus specifically on minimizing the data exchange when doing multi-agent SLAM. Doing that allows us deploying systems in communication-constrained environments, such as caves. In field systems, roboticists typically don't use Wi-Fi, but alternatives such as Zigbee or ultra-wideband. For example, ultra-wideband is practical because it combines communication with time-of-flight distance measurement, which allows to support relative pose estimation. When dealing with limited bandwidths, as provided by Zigbee or ultra-wideband, an interesting aspect of the system is its scalability. How will the data exchange grow as the number of agents grows? In centralized state-of-the-art systems, we have linear scalability because every added agent simply adds more data that's streamed to the central entity. Decentralized systems have a priori less data exchange because they don't need to send all of the information to the central entity. However, when implemented naively, as we will shortly see, their complexity is actually quadratic, meaning that beyond a certain agent count, the data exchange of decentralized system is actually larger than of a centralized system. In my thesis, I have addressed the scalability issue in two ways. First of all, I have shown how to make decentralized place recognition linear instead of quadratic. Then I have also worked on representations for SLAM that allow much more compact data exchange. To give you an example, in our 2018 systems paper, we had 10 agents operating in the world for 1 minute. 2.4 gigabytes of raw data were converted to only 2 megabytes that were exchanged overall. So what is this data exchange caused by in multi-agent SLAM? A priori, every robot only performs visual odometry, converting its own images into its own map. The first data exchange between agents happens with place recognition. Here, if we have, for instance, the image seen on the left by one agent, the goal is to figure out whether any other agent has seen this place. For example, if some other agent has seen the right image in the past, place recognition should return as a place match between these two places and these two robots. Then, once we have those place matches, we will want to establish the relative pose between the agents. If we would then assemble our maps in a naive way, they would not be consistent, because visual odometry tends to accumulate error over time. We can use optimization to get rid of this inconsistency and to increase the accuracy of the map. So we have these three components that exchange data: place recognition, relative pose estimation, and optimization. Let's see how we can reduce the data exchange for each of them. Place recognition is the task of figuring out whether two images are from the same location. Nowadays, this is done using neural networks. Those networks are trained in such a way that if two images are from the same location, the embeddings that is calculated from the input image are close to each other. Whereas if the two images are from different locations, the embeddings are far away. So if we would now take the system and do decentralized place recognition, the naive thing to do would be to ask every other robot. If one robot sees a place that it wants to know whether another robot has seen it, it would calculate its embedding and send it to every other robot. Of course, every robot wants to know whether the place it currently sees has been seen by another robot, and so every robot is talking to every other robot. This means that we have quadratic complexity. If we double the number of agents, we quadruple the data exchange. This is obviously not very scalable. So in the first part of my thesis, I have looked at making this scalable. To do that, I have used a technique lifted from distributed hash tables. Distributed hash tables implement distributed key value lookup. The secret to distributed hash tables is that they use a hashing function, which takes as input the key and will deterministically assign a peer to be responsible to store the value of that key. Then we can input data into the distributed hash table, and we will know which peer to send the data to. And we can query the system by simply only asking that one peer instead of every other. So to apply this trick to decentralized place recognition, the idea is to relate place recognition to key value lookup. To do that, I take the previously seen embedding space and I cluster it in such a way as, for instance, can be seen here. As an illustration, we can imagine that one of the clusters has only images from streets, another cluster has only images from forests, etc. These clusters are now assigned to agents. And in this situation, if some agent sees an image of the forest, it'll send its embedding to the red agent. The red agent will have all of the embeddings that were previously seen in forests and will be able to return the place recognition match. We have asked only one agent instead of every other agent, and the scalability goes from quadratic to linear. There are some limitations to this approach. For example, if the query and the true match are close to each other but in different clusters, this particular instance will not be able to be retrieved. This and some other subtle limitations are discussed in our 2017 paper. Okay, so that was place recognition. That gives us place matches. Let's now figure out the relative pose between agents. If we look at the data exchange, this time it does not depend on the agent count, but on the trajectory overlap. More precisely, we will have to do a relative pose estimate for every place match that we get. I don't think that there is a way to do this in a sublinear manner. However, I have been able to make progress on minimal representations for relative pose estimation. I used the standard approach of extracting 2D feature points, matching them between images, and doing P3P and ransack, which is essentially the mathematical tools that are necessary to convert feature matches, as seen on the top, into a relative pose estimate. When we do that, the amount of data that we exchange is determined by the features that we use, and there is a wide variety of features to pick from in the literature. The problem is that the typical focus of these features is the matching score. Essentially, they extract thousands of feature points and they want to maximize the number of feature points that correctly match. In addition, recently there has been an effort to train invariances, such as viewpoint invariance or invariance to strong appearance changes, such as day to night or seasonal appearance changes. Our focus is very different. We want to have a minimal representation that will simply just allow a good relative pose estimation. So if we take a closer look at the data exchange, the data that is sent around is the feature count times the feature descriptor size, more on that soon, plus the point location. For instance, when using OrbSlam, we can extract 500 feature points. They each have a descriptor of 32 bytes, and then we can use 3 bytes to represent the point location in a reasonable resolution. So if we want to reduce the amount of data that's exchanged, we can either reduce the feature count and or the descriptor size. Let's start with the feature count. One approach to reducing the number of features in a map is to do map compression. In map compression, maps are first built, and then based on observations of how well features were tracked in that map, good features can be kept and bad features can be discarded. The problem is that this is not really good if we want to send a compact query right away. In order to apply map compression, we first need to actually accumulate the map data. So what we instead propose is to train a detector that only detects robust feature points a priori. A feature detector takes as input images, as shown on the left, and outputs a score for every pixel, as seen on the right. Here, the brighter a pixel is, the higher its score. Feature points are then extracted from local maxima in that score map. As you can see, there are many bright dots which are potential feature locations, but we only pick the ones with the highest score as shown with the circles. In our method, this score is calculated using a neural network. Then we have a rather simple training methodology. We start with a random neural network and are able from scratch to reinforce good points and suppress bad points by simply applying the pipeline and looking which of the features that are extracted stick. Using this approach to training, we can get a relative pose with only 50 features. To evaluate that, we take a big dataset with many image pairs and we see what the success rate of establishing a relative pose between these image pairs is. The way that you read this plot is that, for instance, at 50 extracted points, our method is able to extract 80% of the relative poses, whereas the closest baseline is only able to extract that for 70% of the data. As you can see, the more feature points are extracted, the better or the higher the chance of getting a relative pose with diminishing returns. There is a trade-off with viewpoint invariance, as you can see on this plot. On the x-axis, we see the angle difference between two images in an image pair, and on the y-axis, we see the distance in meters between the cameras. As we can see, the further away the images are, the more feature points are required with our method to get a successful relative pose. Okay, so that was the feature count. Let's take a look now at the payload that comes with the features. And that's the descriptors. Descriptors are used to properly match features between images. In this example, we have two images and we have 3 features extracted at each image, and we have 2 correct matches. To get those matches, what is done typically is descriptors are extracted at every point, and then all of the descriptors are compared to each other, and the ones that are closest to each other are matched, giving also a feature matching of the feature points. The problem with this approach is, to do that in a decentralized system, we would need to send all of the descriptors, and they have usually quite a big representation size, typically upwards of 32 bytes. I propose to completely get rid of this data exchange by getting rid of descriptors, which we can do if we rethink the way in which features are matched. The key idea is to not have one feature detector, but to have 128, for example, feature detectors. Then these feature detectors are tasked with each picking only a single feature point. We train these feature detectors such that different detectors pick different points in the same image, but the same detector picks the same point across different images consistently. When we do that, we now have an implicit matching between features from one image to features to the other image. We can simply send a list of all of the feature points that were extracted by our descriptors, and the first one will be matched to the first one in the other image, the second one to the second one, etc. This approach can be implemented using only one convolutional neural network with 128 output channels. Just as before, we train it with image pairs and use a suppression or reinforcement scheme. In our training method, we ensure that each channel picks the same point in both images, and ensure that different channels do not pick the same point in the same image. Let's take a look now at the representation size. We have 128 extracted feature points. We only need to transmit the location of that point in the image, which gives us 384 bytes representation size. Compare that to 17.5 thousand bytes in OrbSlam. Of course, there is a trade-off with performance. And there are also baselines which do some feature compression. However, looking at this plot, we can see that our approach is planted firmly in the top left, meaning that it has a good trade-off between representation size on the x-axis, note that the scale is logarithmic, and the accuracy or the success rate for our dataset as shown on the y-axis. Again, we have a trade-off with viewpoint invariance, and we can see that the further away two cameras are, the less success we have in establishing a relative pose. Okay, so that was place recognition and relative pose estimation. Let's take a look at the final component of decentralized SLAM, which is optimization. In optimization, the data exchange is very difficult to characterize. It does not really depend on the agent count, but in particular it depends on the particular optimization problem and its convergence behavior. Rather than incrementing on existing work in decentralized optimization, I have decided to question whether optimization is needed at all. If we don't need it, our data exchange for optimization, of course, is 0. Consider this map from the 12th century. You can recognize places such as Spain or Italy. What this map shows us is that humans have been able to navigate and explore the world without global consistency, long before there were techniques such as geometric engineering or GPS. Think of your most recent personal navigation experience. Think how you typically navigate from point A to point B. Do you plan a 3D trajectory and avoid collisions in your plan with your 3D map of the world? And then do you track that 3D trajectory using your global 3D state estimate? I don't think so. I think what you do instead, or what I do, is to look at the scene where I'm currently at and just recreate how I moved through that scene, and then do that for every new scene that is encountered. This can also be done for artificial agents using a method called visual teach and repeat. This is a nice conceptual visualization of how visual teach and repeat can be used to navigate a globally inconsistent map. The map consists of several black trajectories, and we can see that it's inconsistent because every violet segment is a place recognition, and the two endpoints of that violet segment are actually one and the same place in the real world. To plan a trajectory now from point A to point B, we can use topological planning in the trajectories, and we can simply assume that we can jump across place recognitions. Then, when we execute that path, we can simply follow the trajectory up to the discontinuity, and then as soon as our plan switches to the other side, we simply continue navigating on the other side of the discontinuity. This also works if we need to take motion dynamics into account, such as would be the case for agile drones. As you can see on the right, for such situations, we can simply assemble a locally consistent view of the map. So if optimization is not required for navigation, what other applications might it not be required for? Let's take a step back and consider applications of decentralized SLAM. Will decentralized SLAM be used for every situation where we have robots or augmented reality devices? I don't think so. In many applications, we will have known environments and powerful communication infrastructure, such as 5G. In such environments, I believe we will be localizing in curated maps. This is the website of Scape, which is one of the first startups to propose the building of such curated maps. It was recently acquired by Facebook. So what I think will happen is we will soon have curated maps that are registered with GPS and optimized on large server farms by companies such as Microsoft, Apple, Facebook, Google, you name it. Whenever we will be able to use such maps, we will do that, and so decentralized SLAM will be useful for all other situations. In particular, it will be useful for unknown environments and in situ deployments in such unknown environments. Of course, one of the first things to do then, when you encounter an unknown environment, is to convert it into a known environment. This is achieved using a method called exploration. Exploration turns an unknown environment into a known environment. One of the main goals of exploration is to ensure that the environment is fully covered. When we're building a map of the environment, we want to make sure that our map is complete. When we have a search and rescue situation, we want to ensure that we find all survivors, etc. So, the final part of my thesis has been about doing exploration without optimization. Standard representations for exploration use a global grid, as you can see here. As the robot moves through the environment, it can take the grid, as shown on the right, and label cells in that grid as unknown, free, or occupied. These grid-based representations work quite nicely as long as there is no drift. but the problem is real systems have drift. If drift is not properly taken into account, we can have failures of our exploration system, such as seen here. As we can see here, the agent missed the opening on the top of the building and thinks that the bottom right part of the map is all that there is to the unknown environment. This can be taken care of using optimization. The problem with optimization is, apart from the fact that it causes additional data exchange, is that also in grid-based representations, it's very expensive to incorporate it. Some remedy is offered by submapping approaches. However, up to our work, submapping approaches also made the default assumption that optimization is needed eventually. Instead, we show that exploration can be achieved also without optimizing the map. The trick to that is to fuse depth measurements only within a locally consistent scope. This locally consistent scope is assembled from depth measurements that are within a certain distance, which reflects the confidence of local consistency, and that includes measurements from across loop closures that are simply transformed in the local frame. Then, when we let an exploration algorithm run on that representation, we can see that it's able to fully cover the environment while leaving the representation happily unoptimized. All that it needs to do is it needs to cover the environment in sufficient place recognitions, which is anyways very handy for taking shortcuts in visual teach and repeat. I am currently working on an extension of this to 3 dimensions. On the left, you see a single volume from a single depth measurement in our representation. In the middle, you see an environment explored using traditional grid-based representations. As has been also observed by parallel work by ASL, the cost of incorporating loop closures in this system is superlinear as the map grows. On the right side, you see this environment fully explored with our representation. In this case, the cost of incorporating loop closures is sublinear, and actually the bottleneck is the loop closure itself. This map might not look very friendly to the human eye, but using visual teach and repeat, it is just as easy to navigate for robots as the one in the middle. So those were my contributions. Let's take a quick outlook at what can be further done to the individual components. In place recognition, I would be interested in exploiting sequential consistency for further compression. If we have a trajectory as shown here, our current approach independently describes each individual keyframe. However, it would make sense that subsequent frames look somewhat similar, and I think it would be interesting to exploit the similarity to compress the representation. In relative pose estimation, I would be really excited about building state-of-the-art invariances into our descriptorless matching approach. If we look at the trade-off between representation size and invariance, our presented work is very compact when it comes to the representation size, but does not exhibit many invariances. State-of-the-art work, in contrast, has not very compact representation, but some of them show really amazing invariances to things like viewpoint changes and appearance changes. I believe that it should be possible to inch towards the ideal case a little bit more, which of course is a compact representation with many invariances. And my first step to doing so would be to modularize our architecture while still being able to train it into an end-to-end manner. And that's it. Thank you very much for your attention. I'm happy to take your questions now. And as a recap, I show a slide with all of the main contributions.